So example 1 from chapter 9. And although this chapter is technically the more difficult chapter, please don't think that it is. It's actually quite simple. You've done all the work to get to this point, and I think this chapter just simply puts things together. Problems like this shouldn't take more than maybe about 5 minutes to read and formulate, because they're very, very straightforward. I think the procedure is clean. There isn't really a lot of guesswork to be done. So let's look at this problem together and see what we're up against. This problem talks about an automobile parts supplier who owns a machine that produces a cylindrical engine part. So there's an engine part that is cylindrical. That is not cylindrical. Here we go. And this part is supposed to have an outside diameter of 3 inches. So there's an inside and outside, apparently, parts to this, something like this. Let's try to put it in the center. And the diameter of the outside ring is supposed to be equal to 3 inches. Just like that. So that's 3 inches. So parts with diameter that are too small or too large do not meet the customer requirements and therefore must be rejected. This is a very interesting problem because it's telling us that, look, anything bigger than or less than a certain specification will be thrown away. So it's already a very strong hint as to what's going to come later. Lately, the company has experienced problems meeting customer requirements. The technical staff feels that the mean diameter produced by the machine is off target. In order to verify this, a special study will randomly sample 40 parts produced by the machine. Perfect. So they didn't tell us they think it's more or less, they just said it's off. The 40 sampled parts will be measured, and if the results obtained cast a substantial amount of doubt on the hypothesis that the mean diameter equals to target, which is 3 inches, the company will assign a problem-solving team to intensively search for the problem. So you've got a part A and B, but what I'm going to do is I'm going to solve this problem straight away, all the way to the end, without looking at these A and B parts. You can do that yourself. And so step 1 is always going to be set up your hypothesis and follow the steps. So here are the steps. Step 1. State the hypothesis. What is our hypothesis? We start off with an HO, and we also have an HA, always. We're always dealing with the population parameter, so we're going to do mu, and mu is here, it's going to equal to 3 inches. We think that the status quo is 3 inches. The alternative is going to be not equal to, I'm going to put this in red to make it more visible, and it's not going to be equal to 3 because, as I've explained in the problem, the research group did not say that the machine is off to the right or the left. It's not producing bigger ones or smaller ones. It just says it's off. So one interesting point I'd like to point out here is that the HO, the signs that will be acceptable for the HO are always going to be with an equality sign within them. So greater than or equal to, less than or equal to, and equal to. Whereas the HA will always have the opposite, greater than, less than, and not equal to. So this also makes your life a little easier knowing that. And frankly, the sign of the HO is not really important. This sign is not important. You can always keep it as equal sign, but a lot of students like to keep it as whatever the alternative is, the opposite, of the alternative. So if the alternative is less than, they'll do greater than or equal to. If the alternative is greater than, they'll do less than or equal to. But that's not necessarily actually needed. You can just keep it as equal to, and it still wouldn't make a difference. Again, the main issue here is for us to determine what the sign of the alternative hypothesis, and this will allow us to choose what type of test we're going to run. Just going to highlight it here. So, state the hypothesis, step 1. Why don't we go ahead and draw something as well so that we can see visually what it's going to look like. So here's my distribution. And I'm going to have mu is equal to 3, which is right there. Okay, step 2. Determine the critical value. So what is the critical value? The critical value is the cutoff mark that you're going to use as your standard. And so the critical value is related to your alpha. So in this particular case, I believe the level of confidence that they're going to go with or is required is alpha is equal to 5%. So if alpha is equal to 5%, and this is a two-tailed test, that means this is 2.5%, and this side is 2.5%, which means that this guy is 47.5%. And so that's what we look up in our table when we're looking for the Z values, because obviously this is a Z value problem because sample size is large, it's greater than 40. And so looking up the Z value, we're going to see that as usual, it's 1.96, and in this case, negative 1.96. So now we've gotten this out of the way. This is our standard. If we find evidence that falls in this region or this region, we can reject HO. So what does that mean, finding the evidence? So step 2, calculate the test statistic, and that's sometimes called your t-stat. So the test statistic is the test you're going to run, and you're going to see if that test exceeds your limit, either upper limit or lower limit. So for us, we're going to call it Z star, just to differentiate it from this first one here called Z, and we're going to solve for Z. And so the first thing we need to know is a sample average. We're going to subtract it from the population parameter, and we're going to divide by sigma over the square root of n, or if we don't know the population standard deviation, we're going to divide it by the sample standard deviation, one or the other. So let's see what happens here. In the problem, they say that the sample of 40 part yields a sample mean diameter of 3.006 inches. Assuming that the population standard deviation equals to 0.16, use the critical value to test. And so they make our life easier. They actually give us the population standard deviation. So for us, we have Z is equal to 3.006 minus 3 divided by 0.16 divided by the square root of 40. Solving for that, you get a value of 2.37. Let me just make this a little smaller so that everything fits in nicely. Just put that right there. Perfect. And so now we've calculated the test statistic. Now, where is that test statistic relative to our cutoff mark? It's 2.37, excuse me. 2.37, does it fall here or does it fall here? Step 4, conclude. Since 2.37 is greater than 1.96, we reject HO. What you can also do is, since the absolute value of 2.37 is greater than the absolute value of 1.96, reject HO. I like to use the absolute values because in situations where there's a negative sign, some people get confused. The answer will always be this way if you use the absolute value. As long as your test statistic is greater than the critical value, you will always reject HO. If we were doing a negative value, if for example the answer was negative 2.37, we'll say that since negative 2.37 is less than negative 1.96, reject HO. So you see the signs flip when you're on either side of the distribution. But if you use the absolute value, it will always be the same decision rule. It would always be the absolute value of 2.37, negative 2.37 is greater than absolute value of 1.96, reject. And so you see that the signs don't change. So in this particular case, let me just make it a little bit cleaner. So since the absolute value of 2.37 is greater than the absolute value of 1.96, reject HO. So we're rejecting HO, basically saying that the diameters are greater than 3 inches. So that's step 4, and that's done. That's the entire problem. So the only step that remains is what is called the p-value. So let's look at the p-value together. And for that, I need to unfortunately erase everything just because it takes a little bit of space. So we're just gonna erase all of this here. And this one needs a good illustration, so we're just going to make this a little bit bigger, just like that. And so I'm just recreating what we've done before. This is what is called your rejection zone, by the way. And together we've determined that Z is equal to 1.96 here. Z is equal to negative 1.96. And the sample that we have ended up being somewhere here. And the Z value for that was 2.37. So what is the p-value? The p-value is exactly this area right here, everything after your sample average, the standard normal value of your sample average. And so what is the area underneath the curve there? That's a bit of a tricky sort of calculation to do. Not really complicated, but just make sure that you don't make any mistakes on this in the steps that I'm going to explain. So first things first is you go to your Z table. And look up 2.37 in your Z values here and here. And find out what is that probability. So 2.37 should be, so here's 2.3. Take the highlighter. And 2.37 is right there. So they're telling us that the distance from the mean up until 2.37 is 49.11. So this is why we need the illustration here. So the distance from here all the way to this one is 49.11. 0.1111, and all I'm asking you to do is find the remainder. So 50% minus 49.11 is equal to 0.89. So there is a 0.89% probability that you will find a sample that big or bigger just by random chance. And so the p-value is interesting because you can use it to reject or do not reject the population parameter or the hypothesis. Because alpha is equal to 5%, keep that in mind. If P is greater than alpha, then you do not reject HO. If P is less than alpha, then you reject HO. And I apologize for my horrible handwriting. And in this particular case, yes, 0.89 is much smaller than our alpha. To be completely true, we have to compare it 5% versus 0.89 times 2. To always multiply by 2 when it's a two-tailed test. And so that should give us a value that is much less than 5%. And so we can say that based on the p-value approach, we also reject HO since P is less than alpha. And you notice that, if I can just elaborate on this just a little bit more, this is the cutoff mark for, let's use a smaller. So this is the cutoff mark here for your test statistic. And I need to make it much, let me just do it here. So it's here, and you see that the p-value is everything after it. And if the p-value gets bigger, you notice that it gets closer and closer and closer to the cutoff mark. And so it gets closer and closer to alpha. When it crosses that line, it is greater than alpha, because the p-value then would be everything from here to here. And so you could see that when the p-value actually crosses alpha, or becomes greater than alpha, it's already a reject decision. Because when it falls here, you know that the Z will be, it will be somewhere less than 1.96, clearly. Because if this is 1.96, this has to be less than 1.96. And so both of these decision rules, they work in tandem, they work together. They both give you the same answer. So for us, it was right here. The p-value was 0.89 on this side, so almost 1%, and therefore it is less than your alpha, and therefore you reject HO.